All right, finally, type 5. So, type 5 in unit 2 is determining the initial concentration of substance. So, what the question is going to very clearly ask for is the initial concentration or the initial number of moles. But the key thing is that word initial is going to be there. What they're going to give you is equilibrium concentration, or Z. So they're going to give you an equilibrium concentration of one species or maybe multiple species. And then you're also going to be given KEQ. The key idea here is that we call these reverse ice problems. We're going to work backwards from equilibrium. So what are the steps? Well, let's kind of see what we think in here. I've kind of changed the way I do these. I'm going to show you actually two methods for doing these. One's a little bit more algebra heavy and one is less algebra heavy. So what are we going to do? Well, we're going to read the question. A certain amount, question mark, of NO2 was introduced into a 5-liter bulb. When equilibrium was attained, according to this equation, the concentration of NO was 0.8 molar. When equilibrium was attained, the concentration of NO was 0.8 molar. Make sure you're reading that question completely, right? If the KEQ has a value of 24, how many moles of NO2 were originally, now here I made a big deal about them saying initially, but originally can be the same word, put into the bulb? So what we're going to start with is a Rice chart. Anytime you're talking about initial and equilibrium, we make a Rice chart. So we're going to go R, I, C, E. And then my reaction is 2NO and an O2 forms 2NO2. Okay. What information have they given us? Well, a certain amount of NO2 was introduced into the bulb. So you're going to have an initial amount of NO2 initially put into the bulb. When equilibrium was attained, the concentration of NO was 0.8. KEQ is 24. How many moles of NO2 were originally put in the bulb? Okay, so this is all the information that they've kind of given us in the question, but there is actually more. If we know that we're starting with a concentration of NO2, it means that there is no NO and there is no O2 to start, which means we know the initial concentration of NO and we know the equilibrium concentration of NO, so we can figure out what the change is. So we know that this guy is going to go down by 2x because this was originally put in the bulb. This one's going to go up by x, and this one's going to go up by x. So we know at equilibrium, your concentration of O2 is going to be x. And then we know two things. We know that we don't know the concentration of NO2, but we know that at equilibrium, it's going to equal the initial concentration of NO2. Oh, I need to give myself a bit more room there. I'll put that back on a little bit closer, a little bit farther away. Right? So the equilibrium concentration of NO2 is going to equal the initial concentration of NO2 minus 2x. So let's see if we can figure out x. Well, we know that for NO2, 0 plus x is going to give me the 0.800, which means that x must, oh, sorry, that was plus 2x. Almost made a mistake. So we know that 2x is equal to 0.8. So then we're going to divide that 0.8 by 2. And get 0.4. So then we know that the change is that this one went up by 2 x's, so it went from 0 to 0.8. The oxygen went up by 1x, so we actually now know that the equilibrium concentration of oxygen is 0.400. We also know that the equilibrium concentration of nitrogen dioxide is going to be that unknown initial concentration of NO2 minus the 2 x's, so we're going to be minusing 0.8. Well, what are we going to do with this? Well, we also know that KEQ is equal to 24. So if we look at our equilibrium line, we have a known concentration of NO, we have a known concentration of O2, we have an unknown concentration of NO2, but that's my only unknown. Now, here's where I was saying you can do this one of two ways depending upon how into algebra you are. So let's say that this is going to be number 1 and that this is going to be number 2. They're very similar, it's just how you execute the end. Number 1 I'm going to do first is going to be my less algebra heavy. Instead of using this whole expression here for NO2 at equilibrium, I'm just going to use NO2 at equilibrium. Let's not add crazy stuff into this, because we know that if I'm going to do an equation for KEQ, we're in unit 2, for KEQ, it's going to be the concentration of NO2 squared divided by the concentration of NO squared times O2. Okay, so what we're going to be wanting to solve is the equilibrium concentration of NO2, this guy. So let's just solve for that, right? This is the one that's a little bit less algebra intensive. So in for KEQ, I'm going to put in 24. I'm going to keep this my unknown, NO2 concentration at equilibrium squared. And then this is divided by the concentration of NO, which is 0.8, squared, times the concentration of O2. So then to solve this, I'm going to multiply both sides by 0.8 squared and 0.4. So I'm going to do 24 times 0.8 squared times 0.4, which gives me 6.144. So then to get the equilibrium concentration of NO2, I'm now going to take the square root of both sides. So then I'm going to take the square root of that answer, and I end up with a really long number. 2.4787 ... is the equilibrium concentration of NO2. So then we didn't want the equilibrium concentration of NO2, we wanted the initial concentration of NO2. So if we think about the formula, what I've written up here, I'll just give myself a bit more space here. Should never pre-draw lines. Okay, so now if I wanted to find the initial concentration of NO2, I know that the equilibrium concentration of NO2 is equal to the initial concentration of NO2 minus 0.800. So that the initial concentration of NO2 will equal the equilibrium concentration of NO2 plus 0.8. So I've got that answer there, that 2.4787 ... plus 0.800. Now before we do the addition, let's just check our sig figs. So where were we at? With this guy, we had 3 sig figs all the way through, so this would be carried to 3 sig figs. So this would be 2 decimal places minus 3 decimal places. So I'm going to answer to 2 decimal places. So I'm going to hit plus 0.8, and I get 3.28 molar. So the initial concentration of NO2 is 3.28. And that I'm going to call method 1. And I should have left myself some more space. Method 2 is a little bit more algebra heavy, but not a big deal. But it's that instead of finding NO2 initially, or at equilibrium, we are going to use this expression for NO2 at equilibrium. And what that'll allow us to do is find the NO2 initially in one calculation. So instead of having to do a follow-up, where I then had to take the equilibrium concentration and add the 0.8, I'm going to get straight to NO2 initially, right? And it's totally personal preference. So again, we're going to start with KEQ is equal to the concentration of NO2 at equilibrium squared divided by the concentration of NO squared and O2. In for equilibrium KEQ, we're going to put in 24.0. But this time, instead of putting NO2 at equilibrium, I'm going to use this expression here. So I'm going to put in the concentration of NO2 initially minus 0.8 squared divided by, then I know the concentration of NO is 0.8, and I know the concentration of O is 0.4. So then when I do this math, I'm going to do again 24 times 0.8 squared times 0.4, which gives me that same 6.144. But this time, this is equal to the concentration of NO2 initially minus 0.8 all squared. So now I'm going to take the square root of both sides. And I get that same 2.4787 ... But now that's equal to the concentration of NO2 initially minus 0.8. So now I'm simply going to add 0.8, and I end up with the concentration of NO2 initially still being 3.28 molar. So it's just, I don't know, again, personal preference. Like, are you okay with having this like algebraic expression in there? Because then great, you get the answer in one step. If you're like, ooh, this felt better. This was like a type 1 question, right? Where we're finding the unknown concentration of NO2 at equilibrium. And then there was an additional step where you had to then go back and find the initial concentration of NO2. Right? So whatever you feel like doing, they're both equally great. One gets you the answer in one calculation. The other one gets you the calculation or the answer in 2 calculations, but maybe feels a little bit less algebra intensive. So this is just another question. So why don't you pause the video and give this one a go, and then you can come back and I'll work it through and you can check your answer. All right. So, did we finish this? This one actually asked us to find moles. Don't forget. Oh, I don't know how I caught that, right? So when we're looking at this question, it actually said, I even circled it, how many moles of NO2 were originally put in the bulb. So moles is equal to molarity times volume. So we're going to keep this answer that's luckily still in my calculator, this 3.278 ... And then my flask contains, and actually, you know what I'm going to do? Because this is for both of them. So we got to this place where for both of them we had calculated molarity. And then we're going to use that same answer for both of them to say that, okay, then moles equals molarity times volume. So 3.2787 ... times the volume of the flask was 5 liters, or the bulb. So then the number of moles is going to be 16.4 moles. That would have been crappy if that was a test. So always be careful that you've answered what the question asked you for. Okay, sorry, now it's number 2. So again, KEQ is 50 for hydrogen plus iodine gives off 2 HI. A certain amount of HI was added. So this is the unknown. This is your initial concentration of HI. Was added to a 4-liter flask and allowed to come to equilibrium. At equilibrium, 0.2 moles of hydrogen was found. How many moles, again, of HI were originally added to the flask? So we've talked about concentrations at equilibrium. We've talked about initial amounts. So we're going to draw a Rice chart. RICE. The reaction is hydrogen plus iodine forms 2HI. Okay. We know that KEQ is equal to 50. We know that a certain amount of HI was placed into bulb. So a certain amount, the initial amount of HI was placed in the flask. Allowed to come to equilibrium. There was initial concentrations of hydrogen and iodine of 0, and there was 0.2 moles of hydrogen found at equilibrium. So the concentration of hydrogen is going to equal moles divided by volume. So it's going to be the 0.20 divided by the 4.00. So 0.2 divided by 4 gives you 0.050, keeping track of sig figs. So we're going to say that at equilibrium, the concentration of hydrogen is 0.050. So now let's figure out our changes. The HI is going to go down by 2x, and each of these are going to go up by x, which for me right away I can just tell you that x is 0.050, so that's what I'm going to put in for the concentration of iodine. And then for this one, the concentration of HI at equilibrium is going to equal that initial concentration of HI minus 2 times the 0.05. So 2 times 0.05 is 0.1. So it's going to be HI, the amount that you have of this initially, minus 0.10. So then we want to set up the algebra. Well, what's our KEQ equation? Well, our equation would be KEQ is equal to the concentration of HI squared divided by the concentration of hydrogen times the concentration of iodine. And again, this is at equilibrium. So then you have two choices. You can put in 50 for KEQ, and then for HI, you can either put in just HI at equilibrium, keep the algebra a little bit simpler, and then you're going to put in 0.050 for the concentration of each of those, right? Or option number 2 is that instead of putting in HI at equilibrium, you put in HI initially minus the 0.10 for HI, and then you would still put 0.050 times 0.050. Awesome. And then we're just going to solve these algebraically. So 50 times 0.05 times 0.05 gives me 0.125. And you'll notice it's the same answer for both of these. So I'm just going to put it at the same time, because the only thing that changes is the step after the next one. So the next thing we're going to do is take the square root of that, which gives us this big long decimal. So 0.3535 dot dot dot. And then same thing for this one. So then for this one on the left, what you would then have to set up is that equation you have above, which is that the HI concentration at equilibrium is equal to the initial concentration of HI minus 0.10, so that the concentration of HI initially is going to equal the concentration of HI at equilibrium plus the 0.10. So we would put in that answer above. Oh, my handwriting is horrible today. 0.3535 plus 0.10, which is going to give me 0.45 moles per liter, or molarity. And then for this one, we're obviously just going to do that 0.1 so that we also get the concentration of HI initially is equal to that 0.45 molar. Now, this isn't a final answer because I'm not going to forget this time that what they really wanted was the moles of HI. The moles of HI is going to equal that molarity we just got times the volume of the flask. So that 0.4535 dot 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 times the volume of this flask is 4 liters. So times 4 gives you, to 2 sig figs, 1.8 moles of HI. Awesome. So this is a little bit different than the video I'd had up before. If you're watching this again, hopefully this makes it clear and it feels good. Good luck.